All right, let's move on to question 2. Just for time's sake, I can't go over your practice problem answers. So refer to the textbook throughout the week and see if you got them right. Okay. So moving on to the second question. We're calculating the mass of nitrogen just dissolved at room temperature in an 80-liter home aquarium, and we're assuming a total pressure of 1 atmosphere and a mole fraction for nitrogen at 0.78. And so this is a problem where we need to apply Henry's law. And Henry's law essentially says that our solubility, S, is equal to our to some Henry's constant for some gas times the partial pressure, which is P. So we see here that we're given a Henry's law constant for diatomic nitrogen, but we need to figure out this partial pressure. And the way we do that is by using this equation. We find the partial pressure by multiplying the total pressure by the mole fraction. So we see here that our mole fraction is 0.78, and our total pressure is 1 atm. And this gives us a partial pressure of 0.78 atmospheres. And now we can take this and plug that right into Henry's law. So our solubility is equal to our constant, 6.1 times 10 to the negative 4, times our partial pressure. And that gives us this molarity. Now this is in moles per liter, and we have an 80-liter home aquarium. So we need to take this and multiply that by 80. So now we have our moles of nitrogen. Now we need to find the mass of the nitrogen, where we just multiply our moles times the molar mass. And we have our mass of nitrogen. So your practice problem is number 2. Calculate the mass of oxygen dissolved in room temperature in a 60-liter home aquarium. Assume a total pressure of 1 atmosphere and a mole fraction for oxygen of 0.6. And we also have a KH given. Let's give this one a minute. So let's move on to the next example problem. We have an aqueous solution containing 35% hydrochloric acid by mass. We need to calculate the molality and the mole fraction of this solution. So we need to remember some of the formulas that we've learned. So we need to remember our formulas for percent mass, molality, and our mole fraction. So for this solution, we're going to assume that there are 35 grams of hydrochloric acid and then 100 grams total of that solution. So this fits our percent mass of 35%. And from here, now we need to figure out how many moles of hydrochloric acid that we have. So this is the number of moles of hydrochloric acid. Now from here we can go straight into molality and figure that out. We have some moles of HCl, and we're going to put that over our grams or kilograms of solvent. So here, because we have 35 grams of hydrochloric acid, that must mean we have 65 grams of solvent. And whenever we talk about an unidentified solvent, it's usually water. And so dividing this out, we get 1.476 molality. And finally, we can go on to the mole fraction when we calculate the number of moles of water. So first we need to do that. So we have our moles of water. Oops. And then now we can calculate our mole fraction. And so this is our mole fraction. So then your practice problem is we have an aqueous solution contains 22% H2SO4 by mass. Calculate the molality and the mole fraction of this solution. Let's give this one 2 minutes. So let's go on to the next example problem. We have a student has used 255 milliliters of hot water in a lab procedure. Calculate the amount of heat required to raise the temperature from 20 degrees Celsius to 100 degrees Celsius. And we need to remember our formula for heat. This is Q equals mc delta T. And we know also that the mass, or the density of water, is one gram per 1 milliliter. And this is the density for water. So now we can just simply convert from 225 milliliters of water to 225 grams of water. And then here's our mass. We also know the specific heat constant for water, that is C equals 4.184 joules per gram Celsius. And then we can figure out our delta T by subtracting 20 from 100. And from here we can just plug into our formula. And then punch the numbers into our calculators, and we'll find that we get 75.5 kilojoules of heat. So then your practice problem is a little bit different. There's a 40-gram sample of ethanol releases 2952 joules. As it cools down from 50 degrees Celsius, calculate the final temperature of the ethanol. Let's give this one 2 minutes. Alright, so this next example problem is a little bit longer. We need to consider this reaction, this decomposition reaction, and do some chemical kinetics with it. So we need to express the rate of the reaction in terms of the change in the concentration of each of the reactants and products. So we're starting off with a rate. And this rate describes how quickly a reactant disappears or how quickly a product forms. And we can look to our coefficients to help us write this. We see here that our rate, a positive rate, describes the formation of products. And here we have a coefficient of 1, and here we also have a coefficient of 1. That means our rate is just simply the changes in concentration over time. And we need to figure out then our rate for this reactant right here. And we see that here there's a coefficient of 2. So we need to divide our rate by 1/2. And because our rate, our reactant is disappearing, right, we need to add a negative sign. And so for B, in the first 25 seconds of this reaction, the concentration of HBr dropped from 0.6 molar to 0.512 molar. Calculate the average rate of the reaction during this interval. We can remember that we can use this formula right here to help us out. So it's just negative 1/2 I'll do a different line. We just plug that in to our formula, and then we'll get an answer of 1.76 times 10 to the negative 3 molar per second. So for C, if the volume of the reaction vessel was 1.5 liters, was the amount of bromine in moles that was formed during the first 15 seconds of that reaction. So we need to figure out, okay, how many moles did we form to begin with? We have our average rate of the reaction right here. And this is, and here we can figure out how many moles that we actually created. So just multiplying both sides by 15, we get 0.0264 moles over liters. Then here we can just multiply by our volume 1.5. And that is how many moles that we made. Your practice problem is as follows. Consider that reaction and express the rate of the reaction in terms of the change. There's also an average rate. We need to predict the rate of change in the concentration of dinitrogen oxide. Let's give this one 2 minutes as well. Alright, this next example is a pretty quick one. So the tabulated data were collected for this reaction. We need to figure out the expression for the rate law and calculate the value of K. And we also need to figure out the overall order of this reaction. So let's start off by writing the rate law. So we have this equation right here, and we need to figure out our exponents A and B. And we do that by looking at the table and seeing how the concentrations affect the rate. So let's just take experiments 1 and 2. So these top 2 lines right here, and we see that when we double the amount of this NO2, our rate doubles as well. This means that our exponent is just 1. Then when we take experiments 2 and 3, that's these 2 lines right here, or the 2 middle ones, we see that when we double the amount of this fluorine, our rate also doubles. That means our exponent for B is also 1. So our rate law is just as is. Now we need to find the value of K, and we can do that by looking at the table again. Let's take this experiment, the last one, to calculate our value of K. So just rearranging these variables, we get this equation, and then we can just substitute our values in. and that's our value of K. Finally, what is the overall order of this reaction? We have an exponent of 1 for our NO2 and an exponent of 1 for our fluorine. And the overall order is just adding up all these exponents. So this is a second order reaction. So then here's your practice problem. Tabulated data were collected for that reaction. Write an expression for the rate law, calculate the value of K, and find the overall order of the reaction. Let's give this a minute 45. All right, let's go over the next example. The following reaction was monitored as a function of time, and a plot of the natural log of the concentration of A versus time yields a straight line with a slope of negative 0.0045. Let's figure out the value of the rate constant. We need to write the rate law, figure out the half-life, and and figure out our concentration after some time. So let's start with A. What is the value of the rate constant? Our rate constant is just our slope right here. So K is equal to 0.0045. And the reason why this is positive is because this is our graph is of the natural log of A. And A here is obviously going to be decreasing. So we flip the sign to indicate the rate. So now we need to write the rate law for this reaction. R equals K times the concentration of A. And when we substitute our value of K in, we get this. Now we need to figure out the half-life. We need to remember the formula for figuring out the half-life. T1/2, that's how I write half-life, is 0.693 over K. And when we substitute our K in, we get 154 seconds. And finally, we need to answer part D. If the initial concentration of A is 0.25 molarity, what is the concentration after 255 seconds? For this one, we need to use our integrated rate law. Our integrated rate law for the first order reaction is this. And then we need to use our properties of natural logs. And once we plug in our values and then raise everything to the e. So just taking that, calculating it, and raising that to the e power, or raising that to the e. We get this concentration. So then here's your practice problem. And let's give this one 2 minutes. Alright, this next example problem concerns a reaction mechanism. We need to find the overall reaction, identify the intermediates, and write the predicted rate law. So for this overall reaction, we need to figure out what our intermediates are and take them out. So we see here that we have a chlorine as a product on the first equation, and they are reactants in these next two equations. So chlorine is an intermediate. We also see that this carbon trichloride is a reactant here in the second step, and it's a product in the second step, and a reactant in the third step, so that's also an intermediate. Then if we write the overall reaction just without the intermediates, we get this. And this is similar to finding our net ionic equations from Chem 1. So here we can just figure out what the predicted rate law is. We need to figure out what our rate determining step is. In this case, it's step 2, and then write our rate law from that step. Now we do run into a problem here because our chlorine is an intermediate. So now we need to take this and write this in terms of our first step. So we can see that the rate of the forwards reaction is equal to the rate of the reverse reaction because of this equilibrium arrow here. So we write these two equations, and then we can solve for the concentration of our chlorine. And here I just reduced this fraction, square rooted, to just some other arbitrary constant. And now we can take this and substitute it back into our original equation. And here I've just combined these two arbitrary constants into just another arbitrary constant. So your practice problem is, here it is. So this one has 2 steps. And so find the overall order of the reaction, identify the intermediates, and write the predicted rate law. Let's give this one 2 minutes. next example is pretty straightforward. We're looking at an energy profile and we need to answer a couple of questions. So is this reaction endothermic or exothermic? We need to find the activated complex, and we also need to find the activation energy. So let's start with the first question. We see that we start off with some energy up here and end with some energy down here. So we can say that our reaction is exothermic. We need to identify the activated complex. That's where the reaction has reached its activation energy. So let's just call that AC. That's just right here at the top. Then we need to identify the activation energy. That's how much energy we need to actually get rolling. So let's call that AE. So our activation energy is just right here. Your practice problem has a couple more follow-up questions. To answer the following questions based on the potential energy diagram shown below. And let's give this one 3 minutes. Okay, so we're moving away from kinetics and going into equilibria. So here we need to write an expression for the equilibrium constant of this chemical equation. So here, we just simply write what the products are over what the reactants are. So your practice problem has two reactions that you should write the equilibrium constants for. And let's give this one 2 minutes. So our next example problem has us calculating Kc when it gives us Kp and the temperature. So for this one, we just need to remember this formula. Kp equals Kc times RT to the delta N. And here, we just need to solve for Kc, plug in our variables, and we're good. So we just divide both sides by RT to the delta N, and then plug in our numbers. Here we see that there are 2 moles of iodine, and we have 1 mole of diatomic iodine, so our delta N here equals 1. And here, for this constant r, we need to go to our handy-dandy ACS reference sheet and look at the constants. And here, we're going to be using this one, r equals 0.0821. And once we punch the numbers into our calculator, we get a Kc of 2.56 times 10 to the negative 3. So your practice problem is number 11. Calculate Kc for the reaction at 298 kelvins. And your reaction is given here, and your Kp is here. Let's give this one 2 minutes. For this next example problem, we need to consider a reaction and calculate what the value of Kc is. So we start by writing the equilibrium constant expression. So here's our equilibrium constant expression. And we can just plug in our numbers to calculate K. So our concentrations came from what we were given up here. And so we get a value of K of 135.57. So your practice problem is the same. Consider that reaction and find the value of K. And let's give this one a minute. This next question is about Le Chatelier's principle. So we need to consider some reaction at equilibrium and predict whether this reaction will go to the left, right, or remain unchanged after each disturbance. So with letter A, we have COCl2 is added to this reaction mixture. This is in our product, and so when we add products, we're increasing the rate of the reverse reaction. So this goes to the left. If we imagine the original system and add our diatomic chlorine, this is a reactant. And so we're going to increase the rate of the Ford's reaction. So this shifts to the right. Finally, if we have COCl2 being removed from the reaction mixture, that is our product. And when we remove a product, we are decreasing the rate of the reverse reaction. So this shifts to the right. So your practice problem is number 13. Consider that reaction at equilibrium and find whether the reaction would go to the left, right, or remain unchanged after each disturbance. Let's give this one a minute. So we're moving into acids and bases now. So we're going to identify the Bronsted-Lowry acid, base, and their conjugates. So starting off to begin, we can see that our H2CO3, this loses a proton, and our water gains a proton. So here we can see that this, because it donates a proton, this is our acid. And our water, because it accepts that proton, is a base. And then we can write that our hydronium is a conjugate acid, and our HCO3 is a conjugate base. So your practice problem is number 14. Identify the Bronsted-Lowry acid, base, and their conjugates. We have two reactions. Let's give that a minute. So for our next example, we need to write the formula for the conjugate base of this acid. So remember that when we take an acid and we split it, we get a proton and a conjugate base. So then this right here would just be our conjugate base, this fluorine ion. So your practice is number 15. Write the formula for the conjugate base of each acid. Let's give that a minute. This example problem has us determining the concentration of protons and the pH of a 0.1 molar solution of benzoic acid. And we are also given a Ka for this benzoic acid. So now we need to test if we can do our X is small approximation. So if we multiply our Ka by 100, we get something that's smaller than our 0.1 molar concentration. So we're allowed to do this X is small approximation. And here we can just jump straight to the formula. the concentration of protons is the square root of our Ka multiplied by the concentration of our acid. And so if we just plug in the numbers, our concentration of protons turns out to be 2.5 times 10 to the negative 3. Then we need to figure out our pH, which is just the negative log of our concentration. So if we take this concentration and take the negative log of it, we get a pH of 2.59. Very good question on how we actually derive the formula that I presented up here. So we have an acid which makes a proton and a base. Alright, and so when we do our ice table for this, we start out with some moles, or some molarity, of acid, and no products. Let's call this A. Then our change is minus X for our acid, plus X for our proton, and plus X for the base. For this one, let's just assume that all of our coefficients are 1. Then our equilibrium is A minus X. Here we have 2 X's for our proton and base. And so taking this and putting this into our equilibrium expression, we have this equilibrium expression. And we can just simplify the numerator. And here, we're making that X a small approximation. So we don't need to worry about this X in the denominator. So we just have K equals X squared over A. And then just rearranging our variables, and solving for X, then we get X is equal to the square root of the concentration times K. Does that answer your question? Awesome. So your practice problem is number 16. Determine the concentration of protons and the pH of a 0.2 molar solution of formic acid. And you're given a Ka for that formic acid. Let's give this one 2 minutes. So for this example, we need to figure out if this salt will form a solution that is acidic, basic, or neutral. So let's start with iron 3 chloride. So we can write out the salt, and then we can recognize that this dissociates into iron with a 3+ charge and chlorine with a negative charge. For this one, we don't need to worry about the coefficients. So now we write the corresponding acids to these two, or the corresponding acids and bases to these two species. So we get here FeOH3, and we get HCl. And then here's a table of acids, strong acids and bases. We see here that our HCl is a strong acid, and we don't see FeOH3 here in this table of strong bases. So this here is strong, and this is weak. Obviously, on the final exam, you won't have a table of strong acids and bases, so you'll have to remember them for the exam. So now we see that this here is weak, and we know that conjugate acids of weak bases form acidic solutions. For the second problem here, we have sodium fluoride. This dissociates into a sodium with a +1 charge and a fluorine with a -1 charge. And so now we write the corresponding acids and bases. We see here that this NaOH is a strong base, and this HF is a weak acid. And we know that conjugate bases of weak acids make basic solutions. So your practice problem is number 17. Determine if each salt will form a solution that is acidic, basic, or neutral. Let's give this one 2 minutes. Alright, this is a pretty straightforward one. So we need to use an ice table to calculate the pH of this solution. First of all, we need to figure out, okay, can we use our x small approximation? So when we multiply our Ka by 100, we get something that's smaller than our concentration of acid. So it turns out we don't even need an ice table. We can just jump straight to our formula. So if we write our formula and plug in the numbers, we get a concentration of protons of 0.00724. And then here we just take the negative log and then we get a pH of about 2.14. So for your practice problem, that's number 18. Use an ice table to calculate the pH of the solution. Figure out if you can make that extra small approximation or not first. And let's give this one a minute 30. This next example has us writing the KSP for the dissolution of each ionic compound. In this case, we just have one. So, barium sulfate, this can dissociate into a barium ion and a sulfate ion. And so here we can just write our KSP directly. So your practice problem is number 19. Write balanced equations and expressions for the KSP for the dissolution of each ionic compound. Let's give this one a minute. now we're moving into thermodynamics. So we need to calculate the free energy change for this reaction at 25 degrees Celsius. And we also need to know if this reaction is spontaneous or not. So let's start by writing out the formula for Gibbs free energy. Delta G equals delta H minus T delta S. And so from here, we can just plug in our numbers. So here what I've done is converted Celsius to Kelvin. And we need to notice a conflict here. Our delta H is in kilojoules, but our delta S is in joules per Kelvin. So we need to convert our delta H into joules. And we just do that by multiplying by 1,000. So now we can punch our numbers into the calculator and we'll get negative 2.247 times 10 to the 6th power joules. And since this is less than 0, our reaction is spontaneous. So here's your practice problem, number 20. Calculate the free energy change for that reaction at 25 degrees Celsius and determine if that reaction is spontaneous or not. Let's give this one a minute. This next example has us balancing a redox reaction in acidic solution. So first, what we need to do is we need to split our reaction into half reactions. So here are our two half reactions. Then we need to balance for mass. Here we see that our masses are already balanced. There's nothing that we need to add. So our equations remain as is. Next, we need to balance for charge. So we see here our potassium goes from a neutral charge to a +1 charge. So to balance this, we add 1 electron to the product side. Our chromium goes from a 3+ charge to a neutral charge. So here we need to add 3 electrons to the reaction side. And then now we need to multiply by a factor so that we have the same number of electrons for both of these half reactions. So here, we just multiply this top reaction by 3. And our other half reaction remains the same. And then we combine them. And we combine them by adding up everything on the product side and then adding up everything in the reaction side and then adding up everything in the product side. And we have 3 electrons on the reaction side and 3 electrons on the product side, so we can cancel those out. And here is our final balanced reaction. So your practice problem has you balancing a redox reaction in acidic solution. Let's give this one a minute. Alright, moving into nuclear. We need to write a nuclear equation for the indicated decay of these nuclides. So we have U-234 and we're given an alpha decay. So first we need to write this in a different notation. We have our uranium, and referencing our periodic table, uranium is right here. We have an atomic number of 92. And our mass number is given to us here. Now we need to know the mass number and the atomic number of our alpha particle. Which is 4 mass number and a 2 atomic number. And then finally we need to find out what we get after we remove an alpha particle from that uranium nucleus. So we just subtract 4 from 230, which is 200. 230. Then we need to subtract 2 from 92, which is 90. And this is our atomic number right here, so that can help us find our symbol. So here, we have an atomic number of 90, so our symbol is TH for thorium. Similarly, we have nitrogen, and we see here our atomic number for nitrogen is 7. And this emits a positron. So remember that a positron has 0 mass, and it has a +1 charge, or +1 atomic number. This has a positive charge. And so here, we just need to figure out what our mass number and our new atomic number are. So 0 minus 13, or 13 minus 0 is 13. And 7 minus 1 is 6. And so referencing our periodic table once more, our atomic number is 6 here. So we see that our symbol is C for carbon. So your practice problem is number 22. Write a nuclear equation for the indicated decay of these nuclides. Let's give this one a minute 30. Okay. We are running out of time, so there's one final question we did not get to. It's up here, number 23. So I would have a look in the textbook and see if you can figure this out on your own. Just mentioning a couple of study tips for this final exam. Do start studying now. I recommend an hour a day. Go through a chapter and split up your time so you can take breaks and stay refreshed. I do not recommend studying the previous exams for the final. This means both exams in the large lecture and also the previous ACS exams. They're good practice, but I don't recommend using them to learn the material. This review will be on YouTube, so do review that over the week if you have if you want to have something to reference. And do also review concepts from Chem 1. So a lot of what we do here in Chem 2 is based off of Chem 1. Are there any final questions? All right, then that concludes our session. Thank you very much and good luck on the final. Yes, YouTube. It's on the SARC YouTube channel.
Okay, so like all these exact problems or
Yeah.
similar problems?
Yeah, this whole session was recorded.
Okay.
And so
then I think there's another one tomorrow, isn't there? Is it the same thing?
it
or
is Yes, I know Michelle's doing a review. Let me look that up. Her review probably is a lot less strenuous than mine.